motivation for our work at the Institute of Manufacturing Technology is that our idea is to realize, not now but in the near future, a more decentralized production. One of my opinions is that it is really necessary to produce local for local and not to have one production place in the world and then to ship all the elements to another. So I'm a real fan of having the ability to transfer the knowledge, the processes, and to be able to use also the local materials that are available with the local staff members, etc. And in order to be able to do so, we have, of course, to take into account that over the last about 50-60 years, we know that the product cycles became shorter and shorter. A wonderful example for this is, of course, a mobile phone. In former times, we used the same mobile phone for 5 years. Now, every year is coming a new one, and that is a good indicator for shortening of production cycles. But it's the same with the vehicles we use. In former times, we had such a car 10 years. Nowadays, after about 2 to 3 years, we have a facelift. And beside that, we have a lot of derivatives. And this means that we have to use often, or we should use the same tools, the same process chains, but we want to have at the end different products. And that means that we need some flexibilisation, and all with that we have to take into account the resource efficiency, because we only have one planet. And if we take this into account, especially in Germany, automotive industry, of course, is one of the main players. We know that lightweight construction, multi-material design, some functional integration, and also shorter process chains are the most important aspects. And we try to bring together all these aspects and to find a solution how we can realize that. And our idea is to tailor the material properties in order to fulfill all these demands. And if you have a look on the definition of tailoring as it is made in the Cambridge Dictionary, you can see that it is called specially made for a particular purpose. And what does this mean if we talk about forming processes? In this context, it means that we have to adapt the properties of materials in order to enable a specific forming operation and to get a good and robust process chain with a good and successful product at the end. And that means that for tailoring, we need possibilities to adjust not only the geometrical aspects, but also the mechanical properties. And this can be done either by a locally defined heat treatment of the material, so to locally and temporarily adjust the mechanical properties, or we can also have a local adjustment of the blank thickness. And so if we have a look on tailored blanks, we know the first tailored blanks we saw ever in the world has been the tailor welded blanks, for which different or dissimilar materials, dissimilar either in sheet thickness or in mechanical properties, have been joined by welding. A few years later, the first patchwork blanks arrived in the world, where we use a second blank for local reinforcement, and these materials are joined by either welding or gluing. And of course, everybody, all the designers told the engineers, wonderful ideas, but gluing, welding, the weld line, that is a defect within the material, so not so good. Could you please deliver some other ideas? And so it was in the 90s that my colleague Rainer Kopp from the Aachen University, he was the first presenting tailor rolled blanks. So seamless tailor blanks produced in a rolling process, but with one restriction, as you can see it on the slide here, only linear connections between the thicker and the thinner area have been possible. At nearly the same time, a group of researchers coming from Stuttgart and Erlangen, they developed the so-called tailor heat-treated blank, so blanks for which a local heat treatment was used for a local temporary adjustment of the mechanical properties. In all cases, if you have a look also in literature, you can see that all these tailored blanks can be used as process optimized semi-finished products for the improvement of forming processes. So I want to talk about the tailored rolled blanks and the tailored heat-treated blanks. Why? The tailored rolled blanks, as I told you, the idea is going back to Rainer Kopp, and nowadays there is a company called Mubea. They use such blanks also for the production, for example, of B-tunnels or so in automobile industry. But it was our idea about 12 years ago or so that we saw there was a huge number of components, not only in cars, but also in trucks, in lorries, in machines, etc. All such so-called functional components. Nobody is having a real closer look on, but they are produced millions by millions. And so they are very important to take into account if we really want to improve the material efficiency in the world. And so we took two typical examples. On the one hand side, a synchronizer ring, you can see on the left, and a seat slide adjuster, that's the second component you can see. One example here is given by a company Deal, another by a company Feintool, a company from Switzerland. And in all these components, you can see that over the last 30, 40 years, the demands on accuracy, functional integration, the aspect of weight of the components, and also the load-bearing capacity was increasing. And so the conventional production technologies came to a real limit. It was about 10 years ago that many companies said, we reached an upper limit, we cannot enhance these limits. And so this was the time we started thinking about there must be a new way. And as a new way, we said, okay, if we use not the conventional cutting and bulk forming technologies, but also we take into account sheet metal, then perhaps we can realize a combination of sheet and bulk forming operation in order to extend the process limits and to come to an improved forming process for realization of such products. And so what you can see on the right as challenge is that we said it's really important to have a first trial to determine which problems may occur. And as you can see here, folding, grooving, these are the typical problems because of the missing stiffness of the component, for example, of a material backflow that is not wanted. And so our idea was, why not to use the idea Rainer Kopp had many years before, and to enhance also this idea to come to a tailored approach to ensure a sufficient and improved material flow control in such forming processes. And so what we did was, we said, beside such tailored rolled blanks with a linear connection between two areas, it has to be realized to have also circular tailored rolled blanks. And you can see here on the left the first example of such a tailored blank, where we increased the sheet thickness locally also in a rolling process. In this case, it is a mixture between a conventional rolling process and a ring rolling process we had. And doing so, we were able to increase the sheet thickness of the material where we need the material. And the comparison on the right, you can see if we use the conventional sheet, we have the problem of the grooving and folding. And if we use such a tailor rolled blank, we can see that the increase of the sheet thickness will lead to an increase of the stiffness. And so we are able to avoid the failures we saw before. We can improve the quality, because in such a case, that is a component similar to a synchronizer ring, we need some geared teeth at the outside. And so especially the geometry and the accuracy of these gear teeth is very, very important in order to guarantee the function of the component afterwards. And so what we saw is that we can improve the height of such gear elements by about 20 to 30%. That can be correlated directly with the increase of sheet thickness we can realize with a tailor rolled blank. And we can avoid the material backflow that is responsible for the folding of the material. But of course, doing so, we were at the beginning of the real fundamental research work. And so what we did was we investigated if we can apply such a technology on different materials, so steels and aluminum alloys, if we can give a more general indication about the maximum thickening we can realize, and how we will influence the mechanical properties of such materials. And so here you see one example for two steels, a mild steel DC04 and a high-strength steel DP600. I can tell you that also for aluminum alloys we have similar results. So in general we can say in such a rolling operation we can have a local increase of the sheet thickness up to about 30%. And 30% I think is a real good and interesting number, and according with the increase of the sheet thickness, of course, we have a strain hardening effect in the material, what means that we change the mechanical properties, for example, the yield strengths and the tensile strengths, and so also these typical material values are increased by about between 20 and 30%. That depends on the work hardening exponent that is characteristic for the material. As an indicator for this, you can see here some hardness measurements, because you can directly correlate the hardness and the yield strength of the material. After our first success, we were interested in seeing which geometries we can realize. And so we started, as you can see on the left, with a rotational symmetric geometry. That was the real beginning. We had a thickening at the outside. Then we said, okay, let's have also a rotational symmetric geometry on the inside with a reduced diameter. And of course, then we had the idea, oh, there must be also the possibility to realize cyclic symmetric geometry, symmetric and asymmetric. And as you can see, also this is possible always in the same machine using only different tools. And of course, this will open different possibilities to realize different geometries. For example, the geometries, as I mentioned before, so such a, as we call it, circumferential toothing. We can also produce open carriers and improve the formability. Or if we have one look on the next slide, we can see that also it is possible to have such a thickening operation, and so a flexibilisation of the material on both sides of the sheet metal. And if we do so, we can also add, for example, such inner elements for such carriers, internal carriers, which necessary for the load capacity of the component. And so we can combine nearly any idea of thickening in order to improve the forming behavior and also the function of the component afterwards. And of course, that is one way that is especially important for steels. I can really say that's the most effective way to improve and flexibilize the formability of steels. And in contrast of that, the second very important material for design for forming operations is aluminum. We need also a solution for that. The idea behind that are the so-called Taylor heat-treated blanks. What does this mean? The principal idea is going back on a publication coming from the 50s. They made such a local heat treatment and annealing the first time with some copper. And afterwards, in the 90s, it was my colleague Frank Vollertsen with Kurt Lange. They investigated it on aluminum alloys. The idea behind is to use a laser, for example, or any other heating device to have a very short local heat treatment, about 3-4 seconds, and to use the quenching effect and the solutioning effect of aluminum alloys so that we can soften the material locally. As a consequence, we can improve the material flow, we can lower the process forces, and we can flexibilize again the tools we use for different materials. In order to show this to you, I can give you here an example of a drawing tool that is used for drawing outer door panels. And this is designed for the drawing of a steel forming operation. And if you use an aluminum alloy, in this case a participation hardenable aluminum alloy, you can see at once that fracture may occur. As a consequence, we said, okay, we can do such a process analysis using finite element analysis, investigating where in reality the material flow has to come from, where the material flow stops first, and if we do so, we know which areas we have to locally heat treat in order to soften the material and to improve the material flow. On the one hand side, you can follow such a process route in the virtual world, doing all of that by FE analysis. On the other side, you can also do it in reality, because you can transfer the results coming from the FE analysis. If you use, for example, some optimization methods as stimulated annealing, you can transfer the results regarding the mechanical properties of the material to a temperature distribution that is necessary. And if you do so and you apply it to a sheet metal and you perform the drawing afterwards, you can see that you have a failure-free component. And so that was a real good success, leading also now to a transfer into industry. There are some components within cars produced with this technology. And of course, we used it in order to go on and to say, where are the other problems, especially using the aluminum alloys. And one idea have been the Tailor heat-treated profiles, because profiles are more and more important in the field of the body in white. But the problem with the profiles is that, again, wrinkling and deformation and necking may occur. And this can be seen is a result of the compressive stresses and the tensile stresses that occur. And of course, if we have such a wonderful method for the deep drawing operations, then we are sure that we can apply it also on such profiles. And what you can see here is, yes, it works. The most important aspect is that you have to take into account the different stresses that are applied in different areas. So if you have a look on the deduced heat treatment layout on the right, you see that dependent on the layer where we have the tensile stresses and where we have the compression stresses, the heat treatment layout has to be different. And the big plus is that we are able to deduce mechanisms how to design the heat treatment layout. And the three main and important aspects are the reduction of the forming and process forces by the softening of the material, the reduction of the compressive stresses, what means prevention of wrinkling, and the reduction of tensile stresses, what means the prevention of strain localization. And that works also with the profiles. And because of that, we also had the idea that we can use it to adapt the crash performance of materials. And that is, I think, also a wonderful idea if you can not only soften material, but also harden it and use it so that you have, in case of a crash, the possibility to have the best mechanical properties in different areas of the material so that you can have the best safety for the passengers in such a body in white. And at the end, we also had the idea, what's about the multi-material design? Many of the companies working in this field, they complain about the limits of joining different materials, especially steels and aluminum alloys, and especially if we work with high-strength steels, as for example an HCT 780, or also a hot stamp material with a high strength of about 1500 Newton per square millimeters. In all these cases, the ductility and also the strength of the aluminum alloy are not sufficient to work with such a joining technology. And the most important point, of course, is that with an increasing strength of the aluminum alloy, for example, if we use a 7000 series, we have a limited ductility. And so we said, okay, if we have the good results from two other applications, why not to transfer also the results to that? And so what we did was, again, an analysis how we have to locally soften the material in order to improve the material flow, and the effect was exactly as we expected. Again, we can temporarily soften the material, we can improve the material flow, increase the ductility a little bit, so we can come to a successful joining. And so we showed the first time the possibility of joining parts out of dissimilar high-strength materials, especially using the steels and the high-strength aluminum alloys. And so it was my idea to show you that flexibilization of process chains is important, not only for the competitiveness in automobile industry. I think in all areas of industry that is important. One possible way to fulfill these demands is the tailoring of the material properties. We can adjust the mechanical properties of many materials in a wide range, so that we can work with different materials in tools that have been made also for other forming operations. And so it seems to be a real effective method for the enlargement of process limitations. And what is our interest for the near future is to go on not only with the tailoring for one process, but for the whole process chain, because we expect an interaction with forming, joining, cutting operations, and also the assembly. And so we at the moment work on a way how to implement and to use the data from different processes to come to process control for process chains. And that is the idea, so to come in the near future to a zero waste production. So I hope I was on time, and of course I'm open for questions.